standard deviation and reading dot plots. So let's take a look at these 4 distributions and identify what the data sets are, reading the dot plot. So if we take a look, the first data set is pretty boring. All the data values are 10, and there's 1, 2, 3 of them. So if I were to write out data set A, I would write it as 10, 10, 10. For data set B, there's one value that's a 9, one value that's a 10, and one value that's an 11. So to write data set B out, it would be 9, 10, 11. Similarly, data set C, my data values were 8, 10, and 12. And then lastly, for data set D, I've got 2 dots on 9, so that means I have 2 values of 9, 9, 9, and then 1 dot on 12. So my data set is going to be 9, 9, 12. In the next slide, they're going to ask us, how are these data sets, how are these distributions alike? And one thing that we can see right now is that they all have 3 data values inside their distribution. So like we said earlier, all of these distributions are alike in that they each have 3 data values inside their data set. 1, 2, 3, 1, 2, 3, and 1, 2, 3. Another way in which they're alike, the first thing we do when we look at a distribution is look at its shape. These 3, A, B, and C, are all symmetric distributions. D is different from them, but those A, B, and C are all symmetric distributions. And then the next thing we talk about is center. And if you notice for all of these, the mean value of data set A is going to be 10. And so the mean of A, data set 10, notice the mean is 10. The mean of data set B, look at that, it's 10 as well. We've got the 10 in the middle, and the other 2 data values, one is 1 deviation below, the other is 1 deviation above. So the mean would be 10. You can add all the values up, divide by 3, and you'll see that it does come out to 10. So the mean of data set B is also 10. And voila, the mean of data set C is also 10. And lo and behold, the mean of data set D is also 9 plus 9 would be 18, plus 12 would be 30, divided by 3 gives you 10. But better than that, you can see by the balance point, if the mean were 10, you've got 2 standard deviations, not standard, 2 deviations below, and the 12 is 2 deviations above. So the balancing point would be at 10. So this is one of those situations where the mean doesn't tell the whole story, because although all of these data distributions have a mean of 10, they definitely do not look the same. So how are they different? They are different in their spread. Oops, excuse that arrow. So the spread is different. Okay, so let's go through and compute the standard deviation for each distribution. So now, let's check out the spread of these distributions. We can see that data set A is not very spread out at all. All of the data points lie on the mean. So as far as its standard deviation, with the standard deviation being the measure of spread of the observations from the mean, in A, the observations do not spread away from the mean. So our standard deviation in data set A is going to be 0. And then, looking at data set B, it's going to be more spread out than data set A, obviously, because they're not all at the mean. And how far away? This data point is 1 deviation below. This is 1 deviation above. So the average number of deviations in set B, and you can work out the calculations, but that will be 1.0. 1 standard deviation. 1 is the average distance from the mean. Can you guess what the average distance from the mean will be for data set C? If you want to, we can go through the official calculations. The formula for standard deviation is standard deviation, and we're looking at data set C, would be the square root of the sum of all the data values, distances from the mean, and we square those distances and then divide by n minus 1. It's an average. So in the case of data set C, we first need to calculate the square of the distances. So all of our x values are 8, 9, oh sorry, not 9, 8, 10, and 12. And so for all of these, the mean is 10. Square it, subtract 10, square it, subtract 10, and square it. And then we get negative 2, square negative 2, we get 4 here. The distance here is 0. We have 2 deviations from the mean on the last one, so we'll have another 4 there. And then if we add all of these squares together, that will give us our numerator. So add the squares together and we get 8. Okay, so let's go to the formula here, change that. And so now we're going to have our standard deviation of data set C is going to be the square root of 8 over, and n is 3, right? N is 3. So n minus 1 would be 2. So my standard deviation is the square root of 4, which is 2. The average number of deviations from the mean is 2. It was much easier to do that by looking at the data set and seeing there's 2 steps above, 2 steps. The average distance from the mean is 2. But this is the precise calculation. To find the standard deviation for data set D, first of all, before we look at the standard deviation for data set D, we found that the standard deviation for data set C was 2.0. And notice definitely data set C is more spread out than data set B, which is also more spread out than data set A. Data set A is as boring a data set as you can get. There's more variety in B, and then even more variety in C. You can see that spread get bigger. Do you think that D will have more or less variety than C? And for some people, you can kind of look and go, well, the 12s are the same. This 10 has now moved 1 deviation below here to the 9, and the 8's moved up, so it's kind of hard to say. But take your guess, and we'll find out. I'm going to use my calculator to find the standard deviation for D, and to use your calculator, you put your information. For example, if I put in L1, if I write in my L1, again, my data set for D is 9 and 12. So in conclusion, standard deviation is an average distance from the mean, and the more variation, the larger the value the standard deviation is. So hope that helps.